Hello, welcome back. Because of that time constant in this tool, or I don't know what happened to the software. I think there is a limit of the timing. So we can start, we can continue this lithography technique. I think we were on this, we were discussing the exposure system. Okay, so we were here. So proximity printing, we have a gap between the mask and the wafer. The gap is about from 5 to 25 micron, and this separation degrades the resolution. Why? The question arises why. The concept is when there is a gap, like when light will travel, or we make the light to travel from the mask to the wafer, if there is a gap, so the chances of, because now this ray optics comes into picture, and we consider this monochromatic, the UV light is monochromatic in nature, and the monochromatic light will experience the diffraction and the interference, and that can degrade the resolution of the whatever is the pattern is there on the mask. That will be slightly degraded when it will imprint on the actual silicon wafer. So now this resolution can be controlled. The one way is we can decrease the wavelength. Okay, so we can choose the exposure system like that, so that we can achieve the shorter wavelength. So for example, the UV range is there from like 400 to 600, from 200 to 400, or even up to 500 nanometer wavelength we can do this UV photolithography. So starting from 436, like for example G line is there, I line is there. So G line and I line are the different wavelengths in the UV range. So 436 nanometer, I think, if I am not wrong, that is called G line, and 370s, that is I line. And if you further decrease the wavelength up to deep UV range up to 200 nanometer wavelength, so the shorter wavelengths we will use and higher resolution we will get accordingly. Okay, so there is empirical relation between this wavelength and the when we decrease the wavelength, we will get higher resolution, we can say. So if we talk about the projection, next is projection printing. So in projection printing, like we have discussed earlier, we have a distance between the mask and the silicon wafer. Okay, so they provide high resolution without the defect problem. The mask is separated from the wafer, and an optical system is used to image the mask on the wafer. Other is the resolution is limited by the diffraction effect. That is important thing here, because the resolution is limited by the diffraction, and the diffraction effects are this, especially Fraunhofer condition of diffraction is comes into picture when the gap or the distance between the object and the image plane is much higher. So normally what we do in projection printing, we use the step and repeat method. In this, whatever we are having on the mask, whatever pattern is there on the mask, so we do not do the whole exposure of the whole wafer in the single time or in single run. So we expose the small units of the pattern, and this pattern is repeated by either moving the mask or moving the silicon wafer, or both, in synchronization with each other, so that we can use the same reticle and we can produce the steps, and we can repeat it throughout the silicon wafer. So it's not like in contact printing or proximity printing, we do the exposure and whatever the pattern is there on the mask, that will be transferred on the wafer. In projection lithography, we do this step and repeat method. we take a reticle, we do the exposure, then we move the mask in, so that in the next location the same pattern can be repeated, and like that we repeat the same pattern throughout the whole wafer. Now, to understand the optics that is involved in photolithography, we need to understand the basic concepts which we use when we talk about the ray optics. So first is, if the dimensions of objects are large compared to the wavelength of the light, we can treat light as particle traveling in straight line, and we can model by ray tracing. So this concept we will be using in understanding what happens with the monochromatic exposure when we do the pattern transfer, like for the better understanding of the diffraction and other phenomena, optical phenomena that happens during lithography. So when light passes through the mask, the dimension of the object are of the order of the dimension of the mask, and we must treat light as a wave. So these three assumptions we make so that we can understand the optics involved in lithography. So first is Snell's law and reflectivity. So we know that Snell's law states that when from rare to denser medium, when this ray enters from the rare to like medium, from, say, we do not use these terms rare or denser, just for the sake of simplicity we take two mediums, N1 and N2. Suppose this ray is entering from medium of refractive index N1 to the medium of refractive index N2. Okay, so either this ray will bend towards the normal, this is normal, or either it will bend away from the normal, depending upon the kind of the medium we are dealing with. Say for example, if this is rare and this is denser, so it will bend away from the normal, and if it is N1 is higher than N2, it will bend towards the this perpendicular. Okay, so this concept is quite useful because the medium we are using, the optical, like the photolithography is taking place simply like okay, so like we are doing photolithography in the clean room. Okay, so clean room, in clean rooms we are dealing with the clean air is there as a medium. So whatever optics we are using in the clean room, that is entering from the air to the material. This is photoresist or photoresist of polymer or X-ray resist or E-beam resist. Okay, so basically from the air to the photoresist. So now, because the resolution depends upon the medium from which these rays are coming, either these are UV rays or X-rays or E-beam. Okay, the another thing is it depends upon the numerical aperture of the lens, and another parameter on which it depends is the depth of focus. These three parameters are main, and N1, if I am searching from for the relation, or if we find it, we can better understand these things. Otherwise, what happens, say, so if your N1 is high, so if N1 is high as compared to N2, say instead of air, if I use some other environment or the material of higher refractive index than air, it will give us the better resolution. So this is an assignment for you to find out what is immersion lithography. That is directly related to this concept, immersion lithography. So immersion lithography is the modified form of the optical lithography to get the better resolution for the for the miniaturized devices. So where we can have better resolution with more accuracy. So immersion lithography is being done inside the water, because the refractive index of the water is higher than the refractive index of the air, and higher refractive index will give you the better resolution, or like lower features of the pattern you can fabricate using the same system. Another is numerical aperture, NA. So, and the bigger is the lens, the more light it can collect. Numerical aperture of the lens is the quality of the lens to collect or to grab the more and more light. So bigger is the lens, more light it can grab, more accurately it can give you the image. Okay, so bigger lens is also a solution for better resolution. Okay, this is Young's slit experiment and formation of this we can discuss later. So now, because except in contact printing, both in proximity and in projection specimen, we use this concept diffraction of light, and this is the drawback of these two systems instead of their advantage. But the resolution limit is put by because of this concept, diffraction of the light. So I hope that we all know at this stage we know that what is diffraction, but for for the sake of understanding these things in better, we can repeat this thing. So diffraction, when this is related to the bending of the beam, when a monochromatic light pass through any single slit or any pattern or the open window, so from the edges it bends from the edges. This property is called diffraction of the light. Okay. And this can be better explained in this picture. So these are the wavelets, and when they pass through the single slit, they will be from the edges, they will be bent away. So at the image plane, they will be creating maximas and minimas. So maxima is where the intensities of the light is maximum, and minima is where the intensity of the light is minimum. So alternate maximas and the minimas will be formed on the image plane. And so the diameter of the central maxima, which is formed on the image plane, is given by this diameter of the central maxima is dependent upon the wavelength, the focal length, wavelength of the light we are using, and the focusing lens diameter. D is the diameter of the lens. So this is nothing but numerical aperture. Okay. So this is the relation. Diameter of the central maxima is related to the wavelength of the light, the focal length, and the numerical aperture of the lens. So from this, if I say that wavelength of the light is very small, means this term will be, if this will be less, this will be high, because they are inversely proportional to each other. And if I say I decrease the wavelength of the light, so smaller lambda will put a limit upon the sorry, let me correct myself. See, diameter of the central maxima is inversely proportional to the focusing lens diameter. This is numerical aperture, we can say. So bigger lens is less diameter of the central maxima, less wavelength of the light or shorter wavelengths of the light, again the diameter of the central maxima will be minimum. So this this is there. So this minimum, the smaller the diameter of this central maxima, higher chances of separation of the image. So image separation will be clear if this maxima is smaller. So two consecutive patterns or two consecutive transparent windows or the open areas will be separated with each other finely. And as we have discussed it earlier also, Fresnel and Fraunhofer are the two conditions of the diffraction. In Fresnel diffraction, the image plane is near the aperture and the light travels directly from the aperture to the image plane. And in Fraunhofer diffraction, the image plane is far from the aperture and there is a lens between the aperture and the image plane. This Fresnel diffraction applies to contact and proximity printing, while Fraunhofer diffraction applies to projection systems. These are two diffractional conditions for Fresnel and Fraunhofer depending upon the distance between the image plane and the object. So if we denote this resolution is the, as we can see, this is related to the diameter of the central maxima. So smaller the diameter of the central maxima, better is the resolution. Means smaller the this maxima diameter, clearly we can resolve the two features on the image plane. And this is related to sin alpha, n sin alpha. This is n is the refractive index of the material between the object and the lens. Alpha is the half angle of the diffracted light. Okay. So for air we take n is equal to 1, and if we can increase this n, we can have smaller resolution, better resolution. And in the continuation of Fermi diffraction, n is the n sin alpha. So this resolution, we can denote it 0.61 into lambda divided by numerical aperture, and this 0.61 we can denote it by some constant k1. Okay, so for practical systems, this value of this k1 lies between 0.6 and 0.8. So resolution will be dependent upon the the wavelength of the light we are using and the numerical aperture of the lens. So from this result we can conclude that we get better resolution, the smaller values of R, with shorter wavelengths of the light and lenses of higher numerical aperture. And this concept of depth of focus, because depth of focus is also related to the numerical aperture. Here we can see depth of focus is in simple terms, if we say like we are taking a picture of an object which is at some distance from us, and we have to take the picture of suppose this is a tree and I have to take a picture using camera from some distance. So depth of focus is the distance which I use to focus the object. Like in this case, in our case, suppose this is tree and I want to focus it using my camera. So the distance between the object and the lens, when the object is exact in focus, that is called the depth of focus, and depth of focus is a key parameter in deciding the resolution in lithography. So we can see the bigger lenses, because depth of focus is inversely proportional to the square of the numerical aperture of the lens. So bigger lenses will give you smaller depth of focus. So we have to make trade-off. We have to take we have to optimize the depth of focus, because we cannot increase the lenses just to get the better resolution, because in that case our depth of focus will decrease significantly, and that is not required. Again, there is a practical constraint in using bigger lenses. So the best alternate to get the better resolution, either you decrease the wavelengths or you do the same lithography using some higher refractive index material, like we do in immersion lithography using water instead of air. So in this Fraunhofer diffraction condition, we see that the central maximum the diameter of the central maxima should be as minimum as possible to separate the two features on the image plane. So now another parameter is that is again critical parameter, modulation transfer function. In deciding the resolution, the separation of the two features on the image plane, we modulate the whatever pattern is there on the mask. We try to modulate it using certain concepts of optics. Suppose like we have talked about the contact printing. In contact printing, let me show you one figure if I have. Okay, so this is clear from this figure. When the mask and the wafer are in close contact with each other, the intensity of the illumination at the edges is the same as it was at the mask. So the intensity of the light is the same, almost same. Whatever it was on the mask, it is there on the image plane. It means on our wafer. But if we increase the gap between the mask and the wafer, the intensities from the corner will keep on decreasing. So in case of proximity, it will be slightly blurred at the edges, but in case of projection printing, the maximum intensity will be only in the middle of the image plane. So sharply it will decrease at the edges, and this variation in the intensities in the center and at the edges of the image plane will give you the blurred or like not clearly separated image from each other. So this is the main limit of the diffraction when we talk about the projection printing system. So to avoid this, ideal condition is there for this. We need to modulate the intensities. So what we want, what is desired, we do not want to decrease the intensities as we go towards the edges of the image. So ideally it should be same as it was in the contact printing, but because of this physics, this diffraction involved in projection printing, we cannot neglect this, but we can optimize this by optimizing the distance between the mask and the wafer. So we need to keep the value of the modulation transfer function between 0.5 to 1. Ideally it should be 1, but anything greater than 0.5 will be okay. And one more solution to achieve the better resolution is the phase shift mask. That we will discuss in the next slide. Next lecture. Or